The main trouble with the greedy improvement in the control loop is that we are going to stay explored once, and then we're going to exploit it forever. This is not a good idea. A better idea is that you just go for epsilon-greedy approach. So what is the epsilon-greedy approach? This is quite simple. So, well, given the estimate that you have action value. You can decide for the optimal action based on that. You know that this estimate is not a good estimate, right? There are a bunch of states you have never seen yet, right? So the thing that you are going to do, at every single state that you get, with some chance epsilon, which could be some small chance, you just play randomly, so you choose any action, or you, with the chance 1 minus epsilon, once again, the main idea is that you play optimal based on the estimate that you have with the chance 1 minus epsilon, and you play randomly with the chance epsilon. Okay? Now, what is the benefit here is that every time you get into a state, well, your estimate tells you go this direction, right? And you can maybe this is not the good one, so let me just randomly go some other direction, see what's happening, right? It's like you want to get to the door, and yeah, you do. If I go this way, it's going to end me with the door, right? But maybe this time when I'm in between, every single step that I take, I would say, okay, maybe this direction is also good, right? So I just randomly go into that path and see whether I end up with a better reward or not, okay? So that is the idea of epsilon-greedy improvement. So basically what we are doing, we are just doing a kind of adding some exploration into our policy. So this is basically what you did in assignment 1, right? For the dummy example we have, you actually did it already in assignment 1, where you just do some exploration with probability epsilon. And then this is going to help you. I mean, you saw that if you just every couple of days, once you just randomly choose to work for a company, eventually you are going to again get to that good limit, right? This is because you're not always closing this for yourself that, well, this is the best to do, right? So maybe my estimate is wrong. Maybe I should improve it by just randomly trying once again. So this is the epsilon-greedy policy. So if I have a particular action value function q hat, then what I'm going to do, I am going to just look at that action value. Now I'm going to look at the action which has the maximum value, and I'm going to do it with 1 minus epsilon, and I do any other action with the chance epsilon over m, right? And you see that why I have plus epsilon m also above, right? So if my tells me that, well, going this direction is the best, right? I am going to go to this direction with chance 1 minus epsilon, right? But epsilon, right? And any I'm going to choose. One of the actions is again this guy, right? So I can go with epsilon for this direction, epsilon for this direction, epsilon for this direction, epsilon for backward. This epsilon over m also adds up to the policy, right? Everybody's clear, right? Questions? Yep. Well, it's not about the model here. I mean, right now you're just building your policy. So your policy is eventually just one table, right? Which says, like, what is this state, and then what is the chance of that action? Building that table. Right. It's possible that for every single 10 days, E would be better. But here, if we do it intermittently, eventually we will get a chance when randomly the right. Yeah, I mean, if you assume that things are happening independently, then the probabilities are the same, right? but what you say is when you have a sort of correlation. Like if I got your question right, you asked whether I do the first 10 days and the second 10 days, or I just randomly choose one every single day and then go, right? Statistically, it should be the same. If your choice every day is independent and the companies are paying you independently, right? But if they have a temporal correlation, of course, then this is not really. I mean, they are not the same. That makes sense. Okay. Okay, so this is the Epsilon-greedy algorithm for updates. So you are going to just explore more, and this is going to improve your information about the environment, eventually improving your action value. Now, one question that you might ask me is that, well, this sounds nice. I mean, I'm starting to explore, but is there any guarantee that if I do this, then I am eventually going to converge to the optimal policy? And the answer is yes, but can you see why this is happening for this Monte Carlo before I show you the proof? Any guess why this is happening? And when I am saying that it's converging to the optimal policy, it means that if I play forever, right? I mean, of course, I know with a limited number of samples, it's again not necessarily converging. But if you play forever, like the rest of your life, right? Exactly. So if you play with this approach, every single time you have even if epsilon is very small, you have a tiny chance of going to other states as well, right? Now, eventually, when you keep playing forever, then you are covering all possible states, right? And in every single state, you are again covering all possible actions, right? Because you are playing forever, right? And by that, then you are going to estimate this Q function properly, and then you know the right action, optimal policy, right? Whereas in the other case, as we had in the example, it could be that you just stick. I mean, you don't see some other states for the rest of time you're playing, right? Because, I mean, you get the bad estimate first, and then based on that bad estimate, your algorithm is converging to one greedy policy, which is, for that estimate, optimal. So we can actually prove this, and if I want to prove this, how can I do that? Any idea? Yes, but what I am doing, each time I am updating with the Epsilon-greedy algorithm, right? So I have one policy pi. I just play with that. I get one estimate. I update, right? And one sample, I update. And once I update it, I do Epsilon-greedy, right? Now, the thing that I need to show is that after doing Epsilon-greedy, that new policy, pi bar, which is coming out of Epsilon-greedy update, the pi bar here, okay? This is better than pi. How can I show that? What should I show? Yes? The value is higher, right? So we define policy A, or pi, is better than policy pi bar, or I want to show policy pi bar is better than policy pi, if the value of pi bar is more than value of pi for any state, right? If that happens, this means pi bar, which you get out of Epsilon-greedy, is better than the policy you had before, right? And if you keep doing this, right, you each time improve your policy, and eventually you converge to the optimal policy, right? Everybody's clear, right? Okay, so I need to show that when I am doing the policy pi bar, I am getting a better value as compared to the case where I have policy pi. Now, I start with this equation. So we had this before. You had it in the assignment, right? So I have the action value. This is the action value of policy pi bar, right? If you have this action value, now if you just multiply it with a policy and you average it over all the actions, then this is going to be the value function of your policy pi bar. Everybody agrees, right? Now, the thing that I want to do, I want to open it up given this guy. Can you help me do that? what is the chance of doing this best action? Say this action, which is the best action, is A star. The chance of this guy is this one, right? 1 minus epsilon plus epsilon over m, right? Forget about epsilon over m right now. So 1 minus epsilon, I am doing the best action, right? So it is going to be this guy computed at the best action times 1 minus epsilon plus any other action times epsilon over m, right? So I can write it down in this form, and you tell me whether you can see it. So any action possible, am, any of them, including the optimal one, right, is going to happen with the same chance epsilon over m, right? I can move this direction, any direction I move with the same chance, right? So epsilon over m multiplied with this guy added up is one part of that summation. The other one is that I could go for the optimal policy, right? And if I go for the optimal policy, which is happening with chance 1 minus epsilon, then I am going to only do action A star, right? And the action A star is the best action, the one which is giving me the highest action value. Everybody sees that? Questions? So this is what you get out of exploitation. So you're in a state with chance 1 minus epsilon, you're going to do only this action, right? And then when you do only this action, the value you're going to get is the action value of this action, right? Whereas you're just plain only, you can do any action, and each of them is happening with the same probabilities. So you're going to add. Okay? This happens with 1 minus epsilon. The other one happens with epsilon. So I average them probabilities. Everybody's cool, right? Okay. So this is you might guess that I also had lack of concentration as a student, and you're right. Now, I have this one. Now, one thing that I can say that this guy, this q pi that you see, this is the one which I do. I mean, pi is my previous policy, right? The policy, I got it, I evaluated it, and then, or actually just tested one with one sample, and then based on that, I decided, right? So this q value is actually maximum at this particular point, right? It means that if I put instead of A star any other action, then this q is going to be smaller, right? So if you forget about everything here, everybody else here. So q of this state for this action A star is more than q of any other action, right? Now, if you average this q over any weight, right, it's still going to be smaller, right? Because one of them is A star, which is the good one. The rest of them are smaller, right? And then when you average the maximum value with a bunch of smaller, right? So if I put any w, which is a averaging weight, it means that if I sum them up, they add up to 1, right? If I put any w here, then this guy is definitely smaller than this one. Agree? Now, the thing that I want to do, I want to choose this particular w. Why I'm doing it? Because it's going to work. That's the only reason, okay? But the thing that we want to make sure is that this w is actually adding up to 1. Does it add up to 1? Can you check and tell me? The weight for one action n is policy pi of that action minus epsilon m divided by 1 over epsilon, 1 minus epsilon. What happen if I add it up over actions? So if I add w up over the action, so I'm adding up over m, all the actions, right? So I'm going to add up this guy, right? Right? This 1 minus epsilon is going to come out, right? Doesn't do anything. Remains this guy, right? What is the summation of the policy over all the actions? What is it? 1, because policy is the probability distribution on the actions, right? What is the sum of epsilon over m m from 1 to m? Epsilon, right? Epsilon over m times m, right? So it's going to be 1 minus epsilon divided by 1 minus epsilon. That's 1, right? So this Wm that you see here is eventually averaging weight, right? If I add them up over different axes, then it's going to be 1. Everybody agrees, right? Okay, so now let me just give it back here. So we said that the value of the new policy, pi bar, at one particular state is this guy, right? And then this guy, well, I can write this down. I mean, this is the optimal one, the maximum one. This guy is, Q value of the previous policy pi over all other actions. And then the thing that I can do, I can say that whatever this guy is, whatever this guy is, this second guy, right? That one is more than summation of these weights times Q. Now, I just wait a second to see it. See this summation, the first summation, is the same thing in the second line, right? Correct? Now, this 1 minus epsilon is again repeating in the second line. That's okay, right? But this Q pi at the maximum action, that is definitely more than or equal by sum of some weights times Q, right? We had it here, right? Q at the maximum action is more than or equal by sum of Q's at different actions by some weights, right? And I just put that weight to be this guy, right? And we know that we can do it because it adds up to 1, right? So the only thing that I have done is that instead of this Q at the maximum action A star, I have written it as the average of the Q's with these weights, and then I can say this is more than or equal, right? Definitely, right? Now, you can go ahead and do a bit of calculation. If you do the calculation, you're going to see that this whole expression, because you have Q pi, same term, same summation, you can factor everything out, and it's going to add up to be this guy, right? And this guy is the value of your previous policy at the particular state. Everybody cool? I told you I can do magics. Yeah. So what does it say? It says that your action, policy, your new policy at any state is definitely better than your previous policy, right? And this means that if you keep on doing epsilon-greedy update, you eventually converge to the optimal policy, right? So even though the greedy itself with epsilon equal by 0, like is sticking to the best policy from very beginning, that is not going to converge to the optimal policy. But if you give it an epsilon, which is non-zero, then you're eventually going to converge to the optimal policy, right? And again, it makes sense because you are actually somehow exploring everywhere at the very end, right? The only difference of this approach is that you are not simply randomly exploring the environment, right? You get some estimate of the values, and you keep on doing more than those values, right? Those actions. But you do not ignore the other possible actions, right? You explore a bit them, right? Questions? No question? So this is the epsilon-greedy improvement theorem. So what it says that if you have this policy pi, and you do epsilon-greedy improvement on that, for some epsilon which is not 0, then this pi bar that you get, this is definitely a better policy, right? And if you keep on doing this, then you are going to converge, right? That's cool, right? Now, does it mean if I use a control algorithm, I am going to converge necessarily to the optimal policy? And be very careful when you answer. So this epsilon-greedy improvement theorem, what it says is that if I am in one policy, right, and I do epsilon-greedy improvement on that, right? Just randomly choose one direction or stick to the best one, right? And I improve it. If I do this one enough number of times, then I'm going to come to the optimal policy. That's cool. But in practice, if I am using a control loop, do you think that this theorem is valid? If not, the answer is no. If not, where is the problem? Yep. That is not an issue, actually. That is not the problem, if I got your answer correctly. But no, the problem is with some drawbacks that we have, some limitations that we have. Yes? Okay, that's acceptable, but this is not, again, the point that I say. Like, if, say you have infinite time. Or now, if you have infinite time, then it's a bit challenging, but say you have good amount of time, but not infinite. Is there any specific thing in this whole analysis here that we don't have access to when we are doing control? Exactly, the true action values, right? So it says that, again, if you were evaluating that policy, so here is Q, right? You're not talking about Q hat, right? You're talking about Q. You see that? You're talking about Q here. This theorem is correct when you're able to evaluate it, right? When you are not able to evaluate it, you're going to add a bit of error to your estimate, right? And that error could send you to non-optimal policy as well, right? But again, as your friend said, if you have infinite amount of time, then you are going to converge there, right? Because eventually, when you have infinite amount of time, at some point you start to stick to one policy, and then you get able to estimate that policy properly, right? And then that policy most probably is the optimal policy. Okay? So, moral of the story, Epsilon-greedy theoretically going to work. In practice, again, we are just doing it based on samples, which is not perfect, but given that we have the theoretical guarantee, we're somehow safe to just keep on doing that, right? So this is the control loop using Epsilon-greedy. So what you're going to do, again, you're going to start with some policy. You just update your Q value for one trajectory, maybe one single time. And then after doing that, you just update your policy by Epsilon-greedy, right? And you keep on doing this till you converge. You see no much difference inside your policy. Questions? So this is pretty much what I told you before, right? So in practice, you have estimates, right? And when you do estimates, you might have initially very bad estimates of the action value, right? And starting with that, you don't expect to see like, well, this policy is just getting improved step by step. No, you don't see it initially, right? But as you keep on going, at some point, your examples, if your estimation approach is a good approach, then you are getting a good estimate of the values, and then from then on, you start to see improvement in the policy, right? This is why these graphs for RL is always super noisy, and they go, like the loss goes always up, and then it starts to go down, right? Because first you just try to find out just explore the environment, get some idea, and then you start to just get better estimates and improve. Okay, so, well, this is going to be the Monte Carlo loop when you consider Epsilon-greedy. So basically, this is the same thing as we had before. The only difference is that in line 4, instead of doing greedy, you are going to do Epsilon-greedy. This is going to give you the chance to explore the environment. And as the result, you can converge to a much better asymptotically and optimal policy. Okay? Questions? No question? Okay, so this is the cliff walking. You had it in assignment 1, right? And then just to see the idea why this exploration is going to help you, just look at this guy. So let's say that, I mean, for this one, if you remember, you have a start point, you have a destination, then you don't want to hit these guys, right? And then if you hit them, then you're going to get a big negative reward, and then you start back here, right? And then if you just take one step forward, then you're going to get only -1. and you want to find the shortest path eventually. And this is the optimal solution, right? This guy is also a solution, but this is suboptimal. This is not giving you the best return, right? So it's giving you less return, but you are not getting, you do not lose the game, right? Now, what you can do, maybe you start just playing with the greedy approach. Maybe you start here, and then well, first you have no estimate, right? Since you have no estimate, you just randomly play, right? So you randomly play, you just go up, write down a cost, right? Now you update your value for this particular state, and their pair action, right? So the action value function is getting improved. Now next time you want to start, you would say, okay, first time I went up, then I went right, and then I went down, and then I lost, right? So this time maybe I start differently, right? Because it's still, this guy has value 0, right? This guy has a negative value, right? This one has more value, right? So you're going to go this way, and you're going to hit the wall, right? So again, you get a big minus, correct? So this is also getting out of the choice, right? Next time, you're going to hit the other side, and you keep on doing that, right? But say that you play that, and out of the sudden, it turns out, it happened that you're going to go like this, and you end up, right? Once you end up, the reward that you get, the estimate that you get for any action value pair in between is much higher than anyone else before, right? So this means that if you keep on playing greedy, you would never get into another path, right? You keep on always playing this one, right? Because this one was the only one which gave you the right or the highest values, right? And there's out of that direction. But if you just do action, if you do if you explore, if you do epsilon-greedy, then it would be potentially the choice that eventually at some point you also try other cells, and you end. Actually, you can try epsilon-greedy with sampling for this one with Monte Carlo, and you're going to see that this one is going to converge to the optimal policy because the environment is quite simple. Okay? Okay. Question? No question? So if you got no question, let me just wrap up this part by just talking about the GLIE algorithms. So what the idea is in GLIE, in these algorithms is that, as I told you, when you do epsilon-greedy, you eventually give this chance, theoretically, that you are going to explore all possible actions and states, right? Because sometimes you are going to play randomly. And out of playing randomly, you're going to explore new states, you do new actions, and you're going to get an estimate for those action and state pairs. So one thing that we discussed before, we discussed that if you are doing Monte Carlo, and if you're just talking about one particular policy, right? Then if you can guarantee that you get into every single state and you play every single action in that state enough number of times, so this C was the number of times you see a state S and you do action A when you have K different episodes, right? So if you come up with some approach which makes sure that this number is increasing when K increases, like you have more episodes, every single state in your environment and every single action is getting chance to be explored more number of times. If you have this property, then eventually, when you just sample enough number of trajectories, if you play enough number of times, then you are seeing every single state and action pair enough number of times. You get a good estimate of the action value, and you are finding the optimal you're estimating the right value of that policy, right? So same story going to happen here as well. So what you can say that if you do enough sampling, such that every single time you just get the chance to just get into some new states. And you do new actions there, right? then eventually, at the very, very end, if you theoretically think of doing it infinite number of times, you're going to just explore the epsilon-greedy, you are going to eventually converge to the optimal one. So if we keep playing enough for all the state and actions, then eventually we're going to get into the optimal values and actions, and then this is going to make this algorithm to just converge into the optimal policy. So one point that you should pay attention here is that if we just keep playing epsilon-greedy, then, well, you start playing one epsilon-greedy, right? And then you fix epsilon, and you explore all the possible cases, right? When you do it enough number of times, then you learn the optimal policy. But if you keep with epsilon-greedy, this means that even if you know the optimal policy, still epsilon % of the time, you're just doing randomly, right? So this means that eventually when your algorithm has converged to the optimal policy, you need to drop that epsilon, right? Everybody's clear, right? Yes? Right. Because at every single state with epsilon, what you're doing is follow the optimal one that I know up to now, or I just randomly move, right? And even if you really have concluded the optimal one and you keep on playing that, you're still going to have this, right? You're right. So we need to cut it off at some point, right? Correct? OK. So, but the issue is that what you do in practice, you're not really playing enough number of times, and then you say, oh, enough. OK, I have just learned the optimal policy. Let me stop this epsilon, right? This is not going to happen, right? Because eventually you have so many state and actions that you're not doing most of them. So what can we do? We can start with high epsilon, and then we can gradually reduce it, right? So initially, you keep it 1. So you just play randomly, right? Maybe you estimate after a few steps, you just make it half, right? Next time, you make it 4. You make it 1/8, and so on, right? And eventually, when you go to infinity, right, that epsilon is shrinking, going to 0, and still it gives you enough exploration that you somehow cover the whole environment, right? So this is the idea of what we call a GLIE algorithm. So this is greedy and limit with infinite exploration. It means that you are doing two things. You are keeping some good epsilon every time. This means that you are having infinite number of exploration. You are seeing every single state infinite number of times, a lot. But at the same time, you're making sure that this epsilon is just shrinking over time. And as it shrinks, when you go in limit, you are being only greedy. You are not being epsilon greedy. Right? So greedy and limit when time is fast enough, but you are doing infinite exploration because you have chosen right epsilon at the beginning. And this is what we call a GLIE algorithm. So the GLIE algorithm has these two properties. So it's not necessarily the one I showed you. The one I showed you is a GLIE algorithm, okay? But if you just play with epsilon. But in general, you could have different other algorithms. But the key point here is that for a GLIE algorithm, you need to guarantee that if you play infinite number of times, then you are actually going to meet every state and action pair enough, right? So there is no particular state in this environment which is going to get missed if I play forever. You get this idea, right? So by going to infinity, I don't mean that you really need to see a number of times. If you have one approach, or if you follow one algorithm, which is somehow blocking one particular state, that algorithm is not a GLIE algorithm, right? We have seen the greedy approach for update, right? If you do greedy approach for update, it could very well be that some states will never be seen, right? That's right, right? if you consider the dummy example of company A and B, if you start with B, you're going to play forever with B if you just play greedy, right? Correct? And then it doesn't matter how many times you sample. Even if you sample an infinite number of times, you are never going to see A, right? So this is not a GLIE algorithm, right? Even if at iteration, at sampling number 10, I am going to once see A, right? Still, it could very well be that you just go 1, 2, 3 till 9th to B, then you go to A, and from 11 on, you again keep on going for B, right? Again, if you play infinite, this guy is 1. It's not getting larger, right? So a GLIE algorithm makes sure that if you play like billions of times, at least some hundreds of times you have seen everybody, right? So it doesn't matter if you have seen this guy more or that guy more. If you increase, both of them should eventually increase, right? So when you play enough number of times, every state and action should be seen enough number of times. And the other thing is that when the episode is going to be infinite, right? You just increase or you go for the next trials in time, then your policy is going to converge into the greedy policy. Not epsilon-greedy. Greedy. And the optimal way to play, right? If you know the right choice of, if you know the right estimate of the values. Now, so I think right now, maybe somebody asked that, well, if we want to just make this epsilon, the epsilon greedy is small enough, then it means that we're not going to visit to make it converge, right? To make it, satisfy both the constraints. One of the good choices is 1 over k, right? So first time that I am sampling, I just totally play randomly. Second time, I'm going to do epsilon greedy with epsilon half, right? Third time, 1/3. Fourth time, 1/4, and so on, right? So this chance of exploration is not going to get absolutely 0. It's not going to get super small pretty soon, right? So if I keep playing enough number of times, eventually I'm going to see everybody, right? But when I keep playing like 1 trillion times, then after that, this 1 over trillion is pretty much 0, right? So it's eventually converging to the greedy algorithm, right? So it's somehow satisfying both the cases, both the properties. And this is, if you do epsilon greedy with that epsilon, this is a GLIE algorithm. Everybody's clear? Questions? No question? Okay, so this is the GLIE version of the Monte Carlo. So you basically have the same algorithm, only on line 4. Every time that you want to sample a new trajectory, you just reduce your epsilon. And this is now a safe one to play with, right? So you start with epsilon 1. So first you just explore, you just get a good trajectory, you estimate, you reduce, right? Your epsilon. You just play half of the time based on the estimate you got, half of the time randomly, right? Next time you have better estimate, you reduce epsilon to 1/3, right? 1/3 of the time randomly, 2/3 of the time based on your estimate, and you keep on going, right? Eventually you're going to play greedy, and this is going to converge into the optimal policy.